My name is Reuben Lara. As I mentioned, I'm the manager for the Cyberinfrastructure of the for the high performance computing group here in Georgia Tech, presenting this panel along with Mehmet Belgin. He's our research scientist, fearless leader. And well, Memo, if you want to introduce yourself real quick.
Sure, I'm the research facilitation lead for Georgia Tech's PACE team. PACE is the centralized research computing support for the entire campus. We are not affiliated with it in departments. We cover the entire campus, and we help with everything related to research computing, on-prem, cloud, stational grids. They're all part of our scope. And software is a big part of the operation. And we'll talk more about that.
Thank you. So the let me try to get into the business. Back in 2017 or so, there were new plans for a new data center and whole new things going on here in downtown Atlanta and midtown Atlanta, which it's where we're located. A brand new building was built, a completely new data center was built, and our aging 30 plus years in the old data center was finally coming to an end. So along with that, it came completely new infrastructure, completely new file systems, completely new way of doing things. And we took that as a chance to redesign how we presented the software to the users. In the past version of our cluster, the way that we did it was, well, we didn't have a lot of controls. We had a single file system where we put all the applications, and there was no real version controlling or ways of making sure that whatever is pushed out is what we want the user to see, and there was no real way of us to rolling back whenever we got to the point of if something wasn't completely right. Memo, would you like to comment a little bit more on that?
Sure. In the old environment, it was way simpler because we had one production cluster that's serving the entire campus. But at the same time, we weren't using any automation. Compilations were mostly from the make or CMake level. Replicability was an issue. When we change things, we need to compile things, like we couldn't tell if they're doing the right thing or not. And we developed our own scripts. They are hacks. They would get one software and compile it for different MPIs, different Intel, compilers, Intel PGI, GCC, different versions of MPI, and put Python in the mix, and it would be a real mess. Some of those compilations, they would have, I counted once, one application had 48 different versions to cover all of those combinations. It wasn't sustainable. So we hit that wall, and we just started thinking of ways to do this better. And especially with the new center, we now had the multiple different clusters there. They have different purposes, and they'll need different sets of software. There was no way for us to be able to sustain our support in the old ways.
So as Memo mentioned, we have multiple clusters, each one requiring different collections of software. Some of them have different security restrictions. Some software cannot run on certain clusters. Some users need to be restricted of other types of software. So again, as you might have realized, software is extremely dynamic. There's one thing that you change along the chain, simply snowballs to the end part of that, and increases the number of versions that you need to maintain exponentially. So what we try to do is, well, first of all, sit down with between Cyberinfrastructure, the storage team, and with the RSC team, with the software team, and begin looking at options. How can we do it? How can we make it so that we get out of this endless loop of of complete this control and this array. So after some thought, we said, well, okay, let's try to use the Git model. But then we, as usual, we began seeing, okay, but if we do that, then it's going to get harder for us to maintain. It's going to be harder for us to upkeep. It's going to be, if we use the centralized Georgia Tech GitHub, we're going to put a lot of load on it because there will be a lot of nodes trying to pull from it whenever we have a new release, and so on and so forth. So we got to the point that we said we want to use the Git model. We want to, for each individual package, to be a self-contained entity that we can just say, I want to pull this specific piece, I want to work on it, and I want to push it back, commit my changes, push it back, and make sure that I have all the version history of it. Then we got to the point of how do we scale it? How can we make it so that the thousands of computers that are reading this stuff can work together and can use it at the same time, and that we can push out the different versions that we have. So what we got to the point is, okay, we'll have to use our own version. So let's try to use GitLab, and we chose GitLab more from the point of view of it's open source, it's freely available, and we can create our own server. Another thing that we looked at when trying to use GitHub is that, at least for the internal Georgia Tech GitHub version, there's some restrictions about large file storage, and getting our own GitLab version allowed us to enable that feature, so that if we need to put a complete tarball with all the binaries that we need to rebuild some piece of software, we can do it. Not that we're doing it very often, but we can do it if we need to do it. Another good thing is integrates with LDAP. We don't have to worry about users. We just set up the LDAP integration, and everyone's happy on that end. So the way that we ended up pushing things out to the clusters is that we defined shared file systems, shared volumes that were going to be mounted across the board. So this is a separate volume from where the users keep their home directories and from where the users keep their project data, and also from where users keep the scratch data to run all their processes. The volumes themselves allow us to do deduplication and compression, so that the idea of having a development, test, and production with the same files, well, slightly different files on different levels of release, really didn't use a lot more space. With the file system took care of all the deduplication and keeping things compressed, and we're really using a fraction of what it would take if we just expanded on a regular file system. And the other thing that was very interesting is that this allows us to get things into Git, check it out, put it into the push it out to the development volume, to test on it, make sure that everything is good, then check it in again, do the same thing for the test volume, and then once we're fine and we're happy with how everything's running, we can then push it out to the production volume. And development and testing are completely independent from production. If anything goes wrong on production and we know the package that went bad, we can just roll back that package. We don't have to worry about all the rest of. Right now we're close to 200 separate packages, Memo, or so.
Even more.
So every single thing, every application, it's its own Git package. And when we deploy, we basically go through sequentially through them just to see which ones have changes against what we have deployed on the production side. And only those packages that have any changes are the ones that are actually updated. That has resulted on a very efficient way of doing it. It's really anyone can work on any package. We don't have to worry about the versioning control. The only places where we can have clashes is whenever someone commits something that someone else was working on. But as usual, that's easy to be resolved with checking in and checking out and recommitting things into Git. And another thing that we came up with is using tags. So we not only have different branches for the software, but what we decided is that to be able to say all these packages belong to production on this cluster, we basically put a tag on all those packages. So when it's time to deploy, we just say deploy this tag, and it takes care of selecting all the packages that have that tag, and those are the ones that are pushed out into the cluster. So if we have a cluster that only has GPU systems, if we have a cluster that has the CUI that with protected information, we have another tag. If we having a cluster with AMD processors that require different binaries, we have a tag. So that again, that allows us a lot of flexibility, because we can have under the same package itself, we can have one branch for AMD, one branch for Intel, one branch for NVIDIA. And then when it's time to deploy to the cluster that has any of those technologies, we set the tag accordingly. So again, it has been a very, very flexible way for us to take care of that. We keep doing update. Well, we keep looking for ways to make it better. And this is the last piece that I hadn't mentioned, and the module system. Memo, if you care to explain for it.
Sure. As with most other centers, we use the module system. It allows users to pick what they need and to configure their environment very easily. So the point here is that this differentiation also provided us with a way to customize the user environment depending on the distribution mechanism that's being managed by Git, and they synchronize they go hand in hand. So everything's compatible, everything is streamlined. And when it comes to licenses, different restrictions, security restrictions for different clusters, we can manage that via modules as well. So there's much else I have to add here, but I'd like to, yeah.
And well, the last part of that is what else are we doing? We continue to refine that deployment process to find ways to make it quicker, make it better. We're trying to go. We ended up getting a bit of a complicated tax system that we found that maybe we can simplify it and make it more streamlined. Every time that some new feature of GitLab comes along, we see how we can take care of that. And something that we're investing a lot of time now is to try to get into automated testing of the software. Any piece of software that we put in, we try to set that automated testing to deploy it into a test set, run things against it, make sure that syntax is fine, that comments are fine, that format of the scripting is fine, and then correct anything that is found automatically. And well, and continuous integration and deployment as goes along with that. So that's it. That's us. We really, I think this has helped us save a lot of time, to tell you the truth, and has kept us very flexible. Excuse me, very flexible and open for new things that the users require, new versions that the users require, and for us to be able to deploy anywhere in very quickly.
I would like to quickly touch on how this changed our life. This is the implementation and these are the motivations. But I'd like to also mention what changes it brought to our workplace. First, separation of installation and distribution has many benefits. We were talking about inclusion, diversity, and developing our own talent. What better way to do it is with students. In the past, we had to tell students, hey, this happened at the root level. We cannot share the password with you. You can just do something on your user space. You can just deploy it and feel like if you replicate it and we distribute it on your behalf. And it didn't really help. It wasn't useful. Now that Git talks with LDAP. We have a group. We can assign any users with that group, and it could be students. They would develop these applications efficiently, and they just submit. And if there's something bad with that compilation, something's broken or not working, we can easily roll back. So it's not like a mistake messing up the entire repository. We have those mechanisms to take a step back, and almost like a time machine. It is great. We are benefiting from all of the benefits that Git brings. So it was a big change in our environment. It also made us more confident fiddling with some of those software, testing them. And especially the last slide had this automated testing, which is going to be a game changer. Imagine, the regular practices for good software engineering includes a regression test at the end. For scientific software, it is difficult. We don't have the infrastructure like some institutions do that with Jenkins, but they're difficult to deploy. But with the CI/CD capabilities of Gitlab, will give us a way to define our own tests, define our own success metrics, and deploy them automatically every time we release a new version of a new software, which are fantastic. So here at this point, I'll just pause, and if you have any questions, please just ask them or put them in the chat. We'll be happy to answer them.
Great.
I have a
Go ahead, Mahmoud.
yeah. Thank you for the presentation. I have a question. I'm trying to understand the workflow you have. So those volumes are mounted on each node, and so they are like a shared volumes, and then the users are still using the LMA to load the packages.
So on all the production nodes, we well, to answer your questions on order, they are shared volumes. They are mounted on all the nodes. For the development volume, it's only mounted on the development servers. Same thing with the test, and production is mounted on anything that is deemed a production cluster. We added a few additional settings on the user's profile, so that whenever they run the module system, they're actually pointing to the shared module, shared volume, and looking at all the modules that are loaded there, that are available there. So the user just type module available, and they will get a list of the things that are coming from that shared volume that's available on the head node that the user usually connects to, and it's also available on each of the compute nodes of the cluster.
Got you. Thank you. And if a software, for example, needs GPU, for, let's say, support for a GPU node, the user doesn't have to specify that in the loading. It just, you already loaded that, like a version that works with that specific node spec, right?
Correct. Right now we have a very homogeneous environment. Everything is based on Intel processors and NVIDIA GPUs. So the devices that have NVIDIA, they already have all the drivers and all the libraries in place. However, there can be some different versions that the user needs for the software to run. So we constantly work with the user to make sure that the modules that are available are covering what they need. But it's one of the things that they need to do while they initialize their job, to select the modules that they need loaded as part of for the code to run correctly.
There isn't really a high, fine granularity of control for GPU. Some of those clusters, they will have both versions with and without GPU. For example, LAMPS, right? It has GPU modules. So there's a direct mechanism that controls that. Most of those software modules will offer both, and it's up to the user to select the GPU version if it's running on a GPU.
Thank you.
Thank you.
In the chat, Reed mentions that he really likes your how to acknowledge page. Yeah.
Very, very clever. But I do have a question for you. I'm just curious because this is something that's come up for us on our side. We also do a lot of similar work in terms of providing all kinds of cyber infrastructure and resources and that kind of thing. My question for y'all would be: do you have to work with research teams that host their software out in the open web, say like on GitHub? And are there any special considerations involved in providing cyber infrastructure resources to teams that are based out there, then they bring their code into your environment?
Fantastic question. Like in a dynamic research environment, it always happens. Not all of the software are verified, tested, and well maintained, but they are still as critical for people's success. So we have to find a way to address them. So currently our scientific repository, the PACE repository, only contains supported software. We don't want to go beyond that because it may impact the integrity of the entire clusters. We are asking users to either use their own space for deploying other kind of software, or we create group directories that are shared within the group, which they can populate. So this was becoming a problem. And a couple of years ago, we started thinking about, we are making a lot of effort to keep these software, maintained, but are they really useful? Are they being used? Back then, we had over like 400 packages. We reduced that considerably. So I started a collaboration with one of the departments who are experts on optimizations. And I said, hey, it's not just the users who are important. It's not just the number of users. It's not just the number of groups using them. Or it's not even important how many times a software is loaded from the modules or how long it's running. But what we need to know, combining all of these factors together, what would be the best choice of software that we need to sustain? And apparently, my question could be translated into a multivariate optimization problem. And we worked with a student over there. He was fantastic. We came up with an algorithm, and we actually published this in PERC. So that gave us different tiers. And I'm getting back to your question. The tier 1 is a very limited number of software, but covering majority of the people, maybe like 70 to 80%. And for that tier, we provide all of the support, documentation, testing, we run them ourselves, modules. Tier 2 is the remaining ones, up to like 98% coverage. But we don't provide, because we cannot provide that level of support, but they are still tested and supported. And there's also tier 3, which we refer to as the community tier. So we decided all of the mechanisms that we came up with could be used by these research groups for their individually managed software. So we started collaborations with the main groups on the campus who have been historically providing their own software, and we were able to onboard them. This is not adopted well yet because it requires some learning curve, but we are using the same mechanism. We are offering the same mechanism, the same conveniences to our users to deploy and share their own software with the rest of their group in an isolated manner, and which prevents problems like once a professor left and the storage was flushed, there were important software there, they're all gone. But getting everything Gitlab solves that problem, and it helps greatly in that way. So we are looking for more volunteers to continue that model, but it is available and we are offering it, and some departments already took us for that.
Great. Feel free to put things in the chat and ask questions, or to unmute if you have any questions for discussion. Reed follows up. This discussion is about tiers of support mirrors, word for word conversations we've been having on our team. If you have any documents or resources that explain your emerging philosophy for CI support, I'd love to share them.
Sure, I'll try to find the link to that publication, which is a really good
That'd be great.
summary of what we were doing.
Yeah, and I would love to see that too, because that's all I do all day.
And
Sit at the bridge between research and IT and make deals. So maybe it's the
Right.
crossroads.
Right.
yeah, and it helped us greatly because, as I said, we could get rid of half of the software load without almost no impact on users. And so focusing on that, I'm a big fan of Pareto rule, like 80-20. 80% of the outcome you can establish with 20%, focus on 20%, and that really aligns with that. Well, I'm looking for this. If you have any other questions, no one is asking, are you crazy? Are you using Git for distributing large binary installations? Like, I'm still looking at chat for that question. Would you like to say a couple of words, Reuben, how we are handling that? That we are not really crazy, although we look like.
Excuse me. Well, one thing that we're beginning to explore to try to make things a little faster is that there are some binaries that take a long time to check in and check out of Git. Whenever you do a Git pull, Git push, it takes a good 10-15 minutes to go through all the different files, and usually it's just the binary files that come from the vendor. There's really not a lot that will change. So what we're looking at using is, let's put everything into a tarball. It's a single file that we can just expand whenever we need it. And if it hasn't really changed, there's really nothing to expand. It will just remain there. So that's something that we're beginning to explore, and that will the large file storage from Git. That's really going to help us, because that way we just put one file instead of taking 15 minutes for that to be pulled or pushed into your local copy. It's going to take seconds. So that's something that we want to make sure that it feels what it want that it will feel what we want to do.
Oh, this is great. Thank you for sharing that paper. I will keep a hold of that link for notes for later. Would anyone else like to ask a question or comment about Git large file storage? I'm really intrigued by this. I know people have tried this for data, but I've never considered doing that for code, which seems obvious to me now, but. In V2D2, that's great. Says don't comment with a database with gazillions of nodes at once. That didn't work out. That's great. No, thanks.